I think this is a really nice painting of Benjamin Franklin. Certainly one of my favorite paintings because it shows him flying his kite in a lightning storm. And I like the painting because it has three angels behind him. The angels were obviously a very important part of the experiment because their blessing was needed to avoid getting electrocuted in this kind of a situation. Benjamin Franklin is a very famous American and is known not only for his scientific work, but also as a newspaper editor and publisher, but later as a statesman and American diplomat. This painting by Benjamin West, circa 1816, is held at the Philadelphia Museum of Art. Benjamin Franklin was from Philadelphia, and for a time he was president of Pennsylvania during a period of time when Pennsylvania was a British colony. Ben Franklin was a revolutionary and he signed the American Declaration of Independence and was quoted as telling John Hancock, who had said that they all need to hang together, "Yes, we must, indeed, all hang together, or most assuredly we shall all hang separately." And by hanging, he was referring to the possibility of being executed. The experiment with the kite took place in 1752. Nearly 30 years prior to the American Revolution. The reason behind flying a kite during an electrical storm was to try to answer a very important question that people did not yet know the answer to at the time. The question was this: is the electricity during a storm, lightning, the same kind of electricity as static electricity that we see when we rub two objects together? Or is it a different kind of electricity? People didn't know whether it was the same phenomenon or not. Moreover, Benjamin Franklin didn't actually fly the kite when there was lightning outside. That would have been really stupid, and the kite was not struck by a bolt of lightning. What he did was to find a cloud where he thought it might have a chance later of emitting lightning, and then he tried to fly the kite near such a cloud, hoping to draw down just a little bit of electricity before the cloud would later have the chance of producing deadly bolts of lightning. That's what this painting depicts. Before the cloud had a chance to charge up a great deal, he held his knuckle up near a metal key attached to the string and was able to get a little bit of a spark from it. Then he was able to compare how the spark from the key felt against his knuckle and how he felt when he touched some kind of friction machine and experienced a shock of static electricity that everyone already would have been familiar with at the time. Naturally, the sparking phenomenon was very similar, and it was thus confirmed, in fact, that these two kinds of electricity felt the same, an important discovery at the time. Benjamin Franklin wrote a letter to the Royal Society in Britain, published October 1st, 1752. When the rain has wet the kite and twine so that it can conduct the electric fire freely, you will find it streams out plentifully from the key at the approach of your knuckle, which is exactly the situation captured in the painting. I encourage you to pause the video and read the text of the Franklin letter in his own words. Naturally, the discovery made news around the world, and many other researchers tried to replicate Benjamin Franklin's result. Now, he was a very smart man. He didn't stand on the ground while he did the kite experiment. And although he mentions in the letter that whoever holds the kite string must be standing indoors, readers may not have appreciated that being electrically insulated from the ground was very important. Unfortunately, some experimenters were killed trying to replicate the experiment, like George Wilhelm Richman in St. Petersburg, August 1753, who unfortunately was electrocuted. It may seem strange to talk about lightning when we're on a path to explain semiconductors, but lightning is a very good example of a case where something that's a very good insulator, air, can become a very good conductor of electricity in the case of a bolt of lightning. Later, we will see that the ability of some materials to change from insulator to conductor in a controlled way rather than a spectacular and dangerous way is one of the keys to understanding semiconductors. So to understand these materials, let's now discuss how air, an insulator, can become a bolt of lightning, which is a conductor. I'd like you to imagine for a moment a slightly simpler atmosphere. Imagine that our atmosphere were made up of hydrogen gas rather than the more complicated mixture that we have in reality. It's a nice model because we only have one proton and one electron in each atom. Let's also forget for the moment that hydrogen normally forms the diatomic molecule H2. Let's just pretend that we have only atomic hydrogen present. It's not conductive. Each atom is electrically neutral, not ionized, and it's transparent to visible light. How could a lightning bolt be generated? Imagine the following. I've got a battery hooked up between two electrodes, and I've decided to put a very high voltage on that battery. One electrode is positive, and the other electrode is negative. Now, as that electron is in orbit around its atomic nucleus, you can start to imagine that the orbit will be distorted a little bit, because when the electron is on the right side, it's repelled a bit by that negative electrode. However, when the electron is on the opposite side of its orbit, it's attracted a little bit towards that positive plate, isn't it? If the voltage is high enough, the electron can even be stripped out of its orbit completely. The energy needed to do that is called the ionization potential, and this depends on two things. First, it depends on the voltage difference between the plate. And secondly, the distance between them. In other words, it depends on the electric field strength. And I've got electric field defined in an equation for you, along with the units in square brackets that we might typically use. So throughout this lecture series, when I give equations, I typically give the units too, because it's easier to keep track of everything. So this cartoon here depicts what would happen if that one hydrogen atom becomes ionized enough through the process just described. Strictly speaking, this process isn't even necessary for lightning to form, because there are already a few ions floating around all over the place anyhow. Ultraviolet light from the sun and cosmic rays from outer space can carry enough energy to break apart an atom here and there, and you only need one ion to get the process started. And I think you can immediately see now that we might get a little bit of electrical conductivity because we previously had a single neutral atom. Neutral atoms are not attracted to positive or negatively charged electrodes. But now that the atom is ionized, we have an isolated proton. It's charged. It's going to start moving to the right. We've got an electron. It's charged. It's going to start moving to the left. In fact, it's not only going to start moving, it's going to start accelerating, because this electric field that we've created between the two electrodes imparts a constant force to charged objects. And Newton's second law says that force is mass times acceleration. So in fact, it's going to start accelerating towards the positive plate. The electrons will end up going much faster than the protons because they're less massive. This electron that just got stripped away from its atom, it's going to start moving faster and faster and faster. And depending upon how dense the atmosphere is, it might strike some other atom on its path and give another electron in its orbit a kick, knock that electron loose from its orbit, which would then create a second ion. Then you would have two protons and two electrons, both accelerating towards their respective plates. Those two electrons then move ahead and ionize more atoms. So this creates an avalanche effect, with each ionized atom contributing one more electron, which then ionizes more atoms. Pretty soon, you've ionized the whole path between the two electrodes. This is called avalanche breakdown. Of course, an electron in this situation does not accelerate forever. On average, each electron will accelerate through a certain distance before striking a new atom, which slows it back down. This is called scattering. So although each electron accelerates, then stops, then accelerates, and then stops again, and so on, it's possible to think about each electron as having an average velocity. This average velocity is called the drift velocity, and this velocity obviously depends on electric field strength. Everything else it depends on is lumped together in a term called the mobility. For example, in a gas, what I refer to as the mobility might depend on how dense the gas is. If we have a really dense gas, electrons aren't going to accelerate very much between collisions, and their average velocity will be lower than in a more rarefied gas. Of course, the drift velocity also depends on the electric field strengths. The stronger the field, the faster the electrons on average will move. So now we have a whole ionization channel. We've now made something that can conduct electricity. Electrons moving towards the positive plate, protons moving towards the negative plate. Now, typically only the electrons will carry much of the current. They move a lot faster. The ions can't really enter the electrode, and in a bolt of lightning outdoors in our atmosphere, the ions can't really penetrate the ground either. In either the situation depicted here in the view graph or the situation of a real lightning strike, the voltage difference between the two plates, or between the cloud and the ground, is caused by a buildup of excess electrons, and it's not caused by a buildup of excess ions, so only a net electron flow can really balance the situation. And so the current is related to the amount of charge displaced over a certain period of time. The SI unit for charge is the coulomb. The SI unit for current is the ampere. It turns out that normally clouds are negatively charged, or equivalently, you could say that the ground is positively charged relative to the clouds. So how many coulombs are moving between a cloud and the ground in a typical bolt of lightning? And let's compare that charge to the charge stored in this battery. So this is a standard AA battery. In a typical bolt of lightning, about 50 coulombs of charge is transferred. Now you could convert 50 coulombs directly to the number of electrons by multiplying the number of coulombs times 6.241 times 10 to the power 18. So 50 coulombs is just on average. How many electrons might move between the cloud and the ground? And how many coulombs do you think that this battery can produce over the course of its useful life before the battery is depleted? And compare that to 50. I'll tell you what, over the course of this battery's lifetime, it will displace something like 5,000 coulombs. In other words, this little battery right here can give you about 100 times more coulombs displaced over its life than a bolt of lightning can in a thunderstorm. And you might think, gee whiz, that doesn't seem right. People die when they get struck by lightning, but you're not going to die from this little battery. But you see, this is the difference between charge and energy. And it's very easy for this little battery to push those 5,000 coulombs around a small electrical circuit that's mostly made out of metal, where the electrons are easy to move around. It's easy to push electrons through small circuits, or equivalently, I could say, it doesn't take very much energy to do it. But in a lightning bolt, electrons have to be pushed through a really thick column of atmosphere that acts like a giant resistor. And it's a lot harder to do that. It takes a lot more energy. That's why a bolt of lightning carries a lot more energy, and that's why it's a lot more dangerous. Another important difference is that the energy in a bolt of lightning is released very, very quickly, but the energy stored in a battery like this is released very slowly over its entire use lifetime. There is certainly enough energy in this battery to kill someone, though. But the battery just can't supply it fast enough on its own to pose a danger. But there have been cases of people electrocuted with certain types of circuits which are designed to store energy from batteries like this and then release the energy quickly. An example of such a circuit is the flash charging circuit of a disposable film camera. These can be dangerous, which is why warnings are sometimes printed on the sides of the boxes. In the case of a lightning bolt, we've basically set up a conducting channel through an insulator. The situation here with the two electrodes wired to a battery is obviously rotated 90 degrees with respect to a cloud-to-ground lightning strike. The cloud is typically negative, having SS electrons prior to a lightning strike. Now let's consider the current that's flowing, and specifically the density of the current through the cross-sectional area of the lightning bolt. You know, the bolt of lightning might be as wide as a small tree. So if a tree has half a square meter of cross-sectional area, then that would be A in this equation. J, the current density, has typical units of amperes per square meter. So What all does the current density depend on? Well, it depends on the charge, which is just the charge of a single electron multiplied by the electron concentration, how many of them there are, as well as how fast the charge is moving. If there are more electrons passing through a certain cross-section in any given period of time, there will be more current flowing. So you can think of current, as measured in amperes, as a measure of the number of electrons measured in coulombs passing through a loop surrounding the lightning bolt in any given second. Current density, then, is just a measurement of how concentrated the current is over a given surface area. Once the cloud has kind of dumped all of its electrons to the ground through that conducting channel, then you know that the lightning bolt will revert back to normal air very quickly. And when the lightning bolt has finished, obviously the free electrons are then going to be recaptured by the ions that were left behind. A bolt of lightning, when it's ionized, is not exactly a gas anymore. It's called a plasma. A plasma is a form of matter where electrons have been stripped away. A plasma is electrically conductive, of course, because you have all of these free electrons available that can carry the current. Now, ions can carry the current too, it's just that they don't move very fast because they're a lot heavier than the electrons. The electrons in a bolt of lightning are going to be recaptured by these atomic nuclei, and the electrons will spiral back into their original orbits. Let's consider the solar system again for a moment. If I wanted to get the Earth to leave the solar system, to exit its orbit, I would need to give it some energy. Some alien with a big machine would have to come in and just push on the Earth, and then it would move off. But something has to impart the extra kinetic energy to get any kind of an orbital change at all. But you know, the reverse is also true. If a fast-moving object were to approach our solar system from outside, it would have to find a way to get rid of its excess kinetic energy. Otherwise, it wouldn't be sticking around for too long. It would just exit the solar system again. So when a free electron is recaptured by a proton floating around, the electron has to give up the extra energy that it has. That energy is emitted as light. And that's why you see a flash of light when you see a bolt of lightning. And the column of air simultaneously gets very hot. This heat causes the air to expand, generating a pressure wave which our ears interpret as thunder. This is a video of lightning in really slow motion. The first thing that I'd like you to notice is the formation of the ionization channel. The lightning bolt has not yet hit the ground, but you can see where the air has already been ionized. There's a bit of light emission because we've already a lot of electrons stripped away from their atomic nuclei, and a few of them will be recaptured spontaneously. These ionization paths are called streamers. Now, when one of these streamers intersects ground, we're going to have a really good conducting plasma channel between the cloud and the ground. This one at the center left is going to hit the ground first, and then you get a big flash after the charge gets dissipated very quickly beyond that point. Sometimes, if there's a streamer, it can kind of flash a little bit because charge moves in from other parts of the clouds, and it takes a little bit of time before the electrons are recaptured again. And this entire process obviously happens very quickly. You know, before the invention of the electric light bulb, people considered the use of electrical sparks as sources of light. Because a good filament that could last a long time had not yet been invented, this use of a spark across an air gap was an early form of electric lighting. And one example of that is called the carbon arc lamp, and here's how it works. Basically, it's a situation where you have two pieces of carbon placed near one another with a small air gap between them. You can see it here in an actual diagram of what one of the lamps looked like from a book published in 1909. If you apply a high voltage across the two pieces of carbon, you'll get a little lightning bolt between them. And this gives off a lot of light, and people actually used these as electric lights. The disadvantage of this type of light, though, is that whenever you happen to use the material for your electrodes, it tends to degrade over time in air because air contains a lot of oxygen gas. And carbon doesn't work too badly, but the spark between the two pieces of carbon generates a lot of heat. And when you heat something up in the presence of oxygen, it tends to oxidize or burn. So the carbon is burning, and you can see that this little diagram showing these carbon electrodes, there's a rather long end of the carbon rod here hanging off the tops and the bottoms of the light. And right in the middle, there's the spark gap. And the carbon would burn away over time, increasing the size of the gap and thus changing the strength of the electric field. Someone would have to come and make periodic adjustments to push the electrodes back together, because otherwise the gap would widen too much and the electric field strength would drop to the point that the ionization channel through the air would not be able to be maintained and the spark would be lost. Of course, you can prevent that kind of eating away of the electrodes by enclosing the whole light inside of a gas envelope where you don't have any oxygen present. People knew that, and it was one of the motivations for experimenters in the 19th century to start working on glass light bulbs where the air can be removed. Of course, this ended up leading to modern tungsten light bulbs, the invention of the vacuum tube, and the world's first real computer using the vacuum tubes. But for a time, this kind of carbon arc lamp was the only form of electric lighting. And it must have really been spectacular when it was first invented, because before this lamp, the only real kind of light that people ever had were fires and candles. A carbon arc lamp can put out thousands of times more light than a candle. It could light a whole city square with a sun-like intensity. They must have been really hot, really brilliant. This type of lighting is not particularly efficient. First of all, some of the light emitted is in the ultraviolet part of the spectrum, which isn't really useful because we can't see it. And secondly, it generates heat in addition to light, which is wasteful in a light fixture. But the heat turns out to be useful in other applications. And if you've ever seen arc welding, you probably know that the heat can be intense enough to melt metal. And the light is so intense that welders need to wear eye protection. So these are really bright, but basically they're very simple spark-making machines. In the next video, we'll consider in more detail the light that is emitted when you heat up materials, and we'll look at reasons why some materials emit different colors of light.